Hi guys, this is Qing Song, a PhD student at the Chinese University of Hong Kong. I'm very happy to be here to share our work for utilizing machine learning methods to solve MIMO problems. We achieve a learning-only method for solving multi-cell, multi-user MIMO sum rate maximization problem. First, let me give a short introduction of our background. We would like to reduce the interference in multi-cell, multi-user MIMO communication systems. Typically, we focus on download link in a cellular network where each user is served by one base station. For example, the signal X are sent from base station 1 to user 1 with channel H, but the receiving signal is overlaid with unwanted signal X12, which is signal for user 2, so which is the interference. For this interference reduction problem, adding a further precoding V is a common use technique. For example, in this case, we expect V12 is orthogonal to channel H11. And the signal to interference plus noise ratio, SNR, is a classical metric to evaluate the extent of interference in terms of DZ1. Then the summation over all users lead to the formulation of sum rate maximization problem, which is non-convex and even NP-hard in some cases. In the past decades, there are many algorithms have been proposed. We categorize them into conventional algorithms and learning-related methods. For conventional algorithms, there are two famous ones. Zero-forcing schemes achieve channel orthogonalization with singular value decomposition, which is efficient, but its solution may not be optimal in some cases. The WFC algorithm utilizes block coordinated descent to iteratively solve the problems and achieve sorted optimality. And for the learning-related methods, we divided them into learning-only and learning-assisted approaches. The learning-assisted approaches utilize machine learning methods to replace operations in existing conventional algorithms. So we provide a timeline for learning-related methods till 2023. The learning-only method is first proposed in 2017. A vanilla DN with unsupervised learning with supervised learning is applied. Then from 2020 to 2022, several different machine learning techniques are applied, such as assembling, reinforcement learning, and ground neural networks. However, learning-only methods can only solve degenerated cycle problems. In our practice, they suffer poor optimality on MIMO problems. However, they are efficient with the acceleration of GPU. For learning-assisted approaches, two typical models are proposed by taking WSE as the backbone algorithm. One uses a neural network to approximate matrix inversion in WSE, and the other heuristically approximate matrix operations in WSE. However, although they are sort on optimality, they suffer poor efficiency for the workflow of WSE, where the precoding of users are serially calculated. Then we have a question that can we keep both optimality and efficiency? So we may need to combine the two kinds of learning-related methods, that is learning-only and learning-assisted. We try to improve the learning-only method since the efficiency is more important in real-world scenarios. And the other reason is that learning-assisted approaches are limited by the backbone algorithm, for example, vanilla WSE, on both optimality and efficiency. And how to achieve that? We find that the existing learning-only methods are all black box models. We cannot analyze their failures on MIMO problem. And then we try to learn from the sorted non-learning algorithm, typically it's WSE, and the optimization problem itself to make it a little bit explicit. We first propose a structural solution update method by learning from WSE. First, we find that in each iteration, The computation in WSE can be transferred into one-line form. For example, this is a whole workflow of one iteration in WSE. So given the channel H and the precoding V from last iteration, we first calculate two auxiliary parameters U and W, and then use them to update V. Then we find that we can substitute the equation of U to the third one and get the one-line update of V. And we take the V in the right box as origin and divide the remaining operations into two matrices on left-hand side and right-hand side. Then, inspired by a recent work, we propose to enroll such two sophisticated computation with two learnable parameter matrices, WL and WR. This process can be regarded as enrolling. We can also reuse the result of an existing efficient non-learning method as an initialization. Since the original operations are formulated with channel H and precoding V, we need to construct the WL and WR from H and V as real. We propose to generate them by neural network models. We call this as the modeling part. Next, we propose new dimension expansion and shrinking scheme by learning from sum-rate maximization problem itself. We find that solving the sum-rate maximization problem in a higher dimensional space is beneficial. First, the problem itself will become more solvable if the variables are in a higher dimensional space. The physical explanation is that if we can have enough transmitting antennas, we can use the zinc antenna to serve each user, which is interference-free. And the second reason is that we can increase the dimensionality of precoding V if we have more learnable parameters. This is beneficial in terms of machine learning theory study. Then we achieve a round-trip mapping since we want to reuse the initialization of original V. This is a whole workflow. Is that we need to map our original solution V to a higher dimensional solution V prime, which gives the initialization of V prime. And then after solving V prime, we need to map it back to get the solution of our original optimization problem. Moreover, we need some more requirements for such mapping. Specifically, we expect the equivalence between V and V prime. The ideal expectation is that we have equivalence on optimality. However, this is too strict in learning-based framework, since the optimality of V prime is still non-deterministic and rely on the training. And then we achieve a relaxed version, which is in terms of feasibility on constraints. So we try to ensure that if the solution V in the higher dimensional space is feasible, then a shrinking mapping solution V in the original space is also feasible. However, existing learning-only framework utilize black box neural network to achieve such mappings. They trivially use normalization after the shrinking mapping to keep V feasible. This is easy to implement since the constraints are quadratic. But this violates the equivalence. So we propose a learnable unitary matrix to achieve such expansion and shrinking mappings with one parameter matrix. This matrix allows us to get visible V from visible V prime. Moreover, such a learnable matrix can be shared among all iterations. First, we propose a lemma that any unitary matrix ensures feasibility of sum-rate maximization problems, so which is proved by Van Neuren trace inequality in our paper. Then, with that learnable parameter matrix D, we achieve the expansion mapping to get the parameter H prime and V prime in the higher dimensional space. Then after solving the V prime in the higher dimensional space, we achieve shrinking mapping to get V of the original space afterwards. Now it's time to have an overview of our whole system. as introduced before. We have two main modules in each iteration. After initialization, we first achieve learnable parameter matrix D to achieve initial precoding V prime and the channel H prime from higher dimensional space. Then we apply update module to update V prime with two parameter matrix WL and WR. We apply an encoder and decoder model framework in the model construction to generate such two parameter matrices. And then in the end, we apply the matrix D to get the solution of our original space, that is V. We implement a fixed number iterations. After that, we get a solution of overall T iterations. And the whole framework is trained by backpropagation and gradient descent. In the model construction, we consider it as a multi-agent system, so where the users are regarded as agents and the channels are shared among users. For the feature selection, we select features from optimization problem. So here is a formal definition of sum rate maximization, and the constraint is per cell power budget. We select precoding V and the result of HV as input feature of neural network models. So here is the illustration of encoder-decoder framework. And the encoder achieves feature extraction and fusion, and the decoder achieves feature transformation among users. Then in each model, we group features by their physical meanings and apply different linear models. For example, the target represents the numerator in the SNR equation, and the others are related to the interference in the denominator of SNR equation. So further, we classify the interference into intracell and intercell interference, and also the interference to intercell and the intercell users. And for the encoder, we apply the message passing neural network on the complete graph to exchange feature vectors that is extracted from encoder among users. So the message passing neural network is a graph neural network on complete graph. So this is an explicit feature exchange among users. We further analyze the complexity of our proposed learning-based methods versus WSE by calculating all matrix computations. So here is the basic result. Our complexity is in terms of tunable parameter D, number of receiving antenna NR, and the number of transmitting antenna NT, which is much lower than the complexity of WSE, since the number of transmitting antenna is much less than the number of base station plus users. For the implementation, we follow the open source implementation of complex neural networks on PyTorch, and we will use a zero forcing scheme for initialization. We basically compare our proposed methods with WSE and 3 learning-related baselines, which are 2 learning-assisted by WSE and 1 learning-only graph neural network model. We construct a synthetic cellular network and randomly sample users around base station. For the channel model, we use channel setting in the WSE paper, which are randomly sampled with path laws. So basically construct 3 scenarios with different scales. In the small scales, we have 2 base stations, 4 users, 8 transmitting antenna of each base station, and 2 receiving antennas. And the largest scale has 2 base stations, each use 32 antennas to serve 16 distinct users with 2 receiving antennas. First, we evaluate the optimality over WSE. Our proposed model achieves up to 98% optimality of WSE. And we need to admit that a learning-assisted WSE method named the GCN WSE achieve even higher optimality than WSE, but it suffered poor efficiency. The abolition in blue box, where we either replace our update module with a black box approach or remove our dimension transformation module, both will cause deterioration of our optimality. And in terms of efficiency, we take the inference time of solving 100 different summary maximization problems. From the table, you can find that our proposed model achieves great speed of our WSE. So we also evaluate our dimensional transformation method on an existing learning assistant algorithm that is IEEE. The outperformance of yellow line then blue line demonstrates that our proposed method can also improve its optimality aspect. Now let's conclude our study. From our knowledge, we are the first learning-only approach for MIMO summary maximization. We propose two schemes: structural update and dimension transformation. And we achieve up to 98 optimality and 47 times acceleration of WSE. That's all. Thank you.